Hello everyone, welcome to part 4 for the solution to the Sleeping Beauty problem and other anthropic paradoxes. In this video, I'm going to discuss the first question in the Sleeping Beauty problem. That is, what is the probability of heads when Beauty wakes up in the experiment? Just a quick reminder, please watch the previous videos if you haven't. This answer, although I think is quite straightforward, probably won't make much sense without watching them. The key point of contention between halfers and thirders regarding the question is this. Should we consider being awake now as new information? Is myself being awake at the current moment a valid new piece of evidence favoring the hypothesis that there are more awakenings overall? And the answer to that question is no. As previously discussed, the meaning of now depends on self-identification. It is the moment primitively identified by its immediacy to the subjective experience. By using this concept in your logic, it already presupposes a conscious experience. Therefore, I must be awake. Otherwise, which moment now refers to would be undefined. And based on the same logic, the existence of primitively identified I is also not a valid new information. This reflects our intuition that I would always find myself exist here and now. So the next question would be, where is the mistake in saying there is new information? Because it would always involve redefining the self as something else. Instead of saying they are identified by the primitive perspective, they will change the meaning of self to something else, and then using that new definition in an imaginary impartial perspective. It typically equates the self as the outcome of an imaginary sampling process, like the self-indication assumption does. There are some arguments claiming we can get to the third solution without using any assumptions or switching to the impartial perspective, but as I will show it later, they're ultimately unsuccessful. Examples of this type of argument include the so-called full non-index code conditioning and Michael Tittenbaugh's Technicolor beauty problem. These two arguments are closely related, and my rebuttal works for both, so I'll just use Technicolor beauty problem as an example. Technicolor beauty's setup is exactly the same as the original Sleeping Beauty problem. There is only one additional detail. There is a light in the room where Beauty wakes up, and it can emit different colors. The color will either be red or blue at the time of two potential awakenings. And which color it emits first is determined completely randomly, independent of the coin toss. For example, this can depend on a roll of a die. If it lands on an odd number, it will emit blue first and then red. If it lands on an even number, then red first, then blue. This addition of irrelevant detail shouldn't change the answer to the question. So what is the probability of heads when Beauty wakes up in the experiment and sees the light? The proposed solution is as follows. After waking up, Beauty can see the light. Say she sees blue. Now she learns the new information that there is a blue awakening. Or in another word, when the light is blue, Beauty is awake. This is something not certain when she goes to sleep, because it is possible that the coin landed on heads, so there's only one awakening, and during that awakening the light is actually red. And a Bayesian update based on this new information that there is a blue awakening would change the probability of heads. And we can use the Bayes theorem to calculate the new probability of heads given that there is a blue awakening. On the numerator, we have the probability that there is a blue awakening given heads, which is half, times the probability of heads, which is half again. At the denominator, we have the total probability that there is a blue awakening, which includes two parts. The first part is when the coin landed on heads, which is again half times half. The second part is when the coin landed on tails, where a blue awakening is guaranteed to happen. So we can get the new probability of heads given the new information that there is a blue awakening as 1/3. You can pause the video to check the calculation. This result is actually quite intuitive since it's twice more likely to have a blue awakening if the coin landed on tails, and therefore the probability of tails is twice that of the heads. This argument claims to solve the problem of no new information, and it does not redefine the meaning of now. And the neat thing is, the result will be exactly the same if beauty saw red instead of blue. All the calculation above still holds. We can simply change all the word blue into the word red, and the reasoning still holds. Therefore, even before she sees the light color, she should already think the probability of heads is 1/3. Since no matter which color she sees, the probability of heads will be updated to 1/3. This is a simple application of the reflection principle. I have to admit that this argument looks quite convincing. Nevertheless, it is still wrong. The mistake is that the statement that there is a blue awakening, while it is factually correct and is indeed a new piece of information, it does not warrant the proposed probability update. The argument still treats the primitive identified now as a sampling outcome, just in a less obvious way. This is best explained with a thought experiment. Consider this problem. You know a family which has 2 kids. You take a random sample among the 2 children and found a boy. Note in this sampling process you are not specifically looking for a boy. You're just taking a random sample. Maybe you asked one of the parents to bring you a random child, and you are presented with a boy. Now, what is the probability that this family only has 1 boy? And the answer is obviously half, as it only depends on if the other child is a boy or a girl. With that in mind, suppose you ask the boy whom you just sampled this: on which day of the week were you born? Suppose the boy answered on a Sunday. Now what is the probability that the family only has 1 boy? Obviously this changes nothing, because you haven't learned anything about the gender of the other child, so the answer must remain unchanged at half. But wait a minute. You have just learned this family has a boy who's born on a Sunday. This is brand new information, and we should update the probability based on this new information using Bayes' theorem. On the numerator, there's the probability that there is a boy born on Sunday, given there's only 1 boy, that's 1/7, times the prior probability that there is only 1 boy, which is half. On the denominator, it is the total probability that there is a boy born on Sunday. First case is the 1/7 times half, which reflects the case of just 1 boy, and the second term is just reflect the probability that there is a boy born on Sunday, given there are 2 boys, which give you a result of 7/20. And that is the updated answer that the family has only 1 boy, given the new information that there is a boy born on Sunday. Now this can also be intuitively explained that it is much more likely to have a boy born on Sunday if there are 2 sons. Therefore, the probability of 2 boys is much higher. In fact, the answer is very close to 1/3 and 2/3, like in the Technicolor Beauty's case. It is only different because there is a small probability that if there are 2 boys, they are born on the same day of the week, whereas the color of the 2 awakenings will always be different. If you want to have a closer look at this calculation, just pause the video. And the interesting thing is, the result and calculation would be the exact same if the boy answered any other day instead of Sunday. So even before the boy answers, you should already be certain that the probability of the family having only 1 boy is 7/20. Clearly, this calculation is wrong. The probability should have remained unchanged at half. This example clearly illustrates, while the information that the family has a boy born on Sunday is factually correct and new, it does not always warrant a probability update. If, instead of just learning the boy is born on a Sunday, you actively sample for a boy born on Sunday and found one, then this kind of update would be correct. For example, if you ask one of the parents to bring you a boy born on Sunday, if they have one, and they actually bring one to you, then you should update based on the new information that there is a boy born on Sunday. And in this case, being born on Sunday instead of any other day matters to the calculation. This shows that the two sampling methods, even though they both give the new information that there is a boy born on Sunday, their calculations are different. So in the Technicolor beauty problem, when they argue that we should update the probability a certain way, they are not just doing so based on the information. They also assumed a specific sampling process. So let's go back to the Technicolor beauty problem. What is the sampling process that the proposed probability update corresponds to? And the answer is quite simple. 1/3 would be the correct answer if an outsider actively sampled for a blue awakening and found it actually happened. For example, maybe he decided to check on Beauty when the blue light is on, and found Beauty awake. Then he should update the probability based on the new information that there is a blue awakening. However, Beauty did not perform this sampling process. She could not do so even if she wants to. All she did was wake up in the experiment, and finds out the color of the light is blue. Now, the argument was essentially thinking from an impartial perspective. Imagine a sampling process, and then assumes the primitively identified self as the sampling outcome. It essentially makes the same mistake as the doomsday argument. And the Technicolor beauty problem actually reflects a very common type of argument in anthropic reasoning. The first step of these arguments would be identify the self based on the primitive perspective, based on the immediacy to subjective experience. But they would not discuss the chance of existence of self in this step. In the second step, they will find out some objective features of the self. Then, they will point out that the existence of an observer with such kind of features is new information. Then in the final step, they will update the probability based on that information. They will do so in such a way as if someone from a God's eye view actively sampled, looking for an observer with those specific features, and find out they exist. As discussed above, this actually involves the assumption of treating oneself as a sampling outcome. And this assumption puts the self in a logically unique position, so the argument is not impartial, even though it tries to appear so. A prime example of such kind of argument would be the so-called fine-tuned universe. It uses the existence of life as evidence favoring some hypothesis, increasing their probability. And their typical hypotheses they argue for are A. There is a creator, or B. That there is a multiverse. But none of the probability update is correct. And I plan to discuss the fine-tuned universe in detail in a later video. So the takeaway of this video is the probability of heads when waking up during the experiment is half. Thirder's answer involves switching to an impartial observer's perspective, and requires additional anthropic assumptions, redefining the primitively identified self. In the next video, I will discuss the second and third question of the Sleeping Beauty problem. Namely, what is the probability that right now is the first awakening? And what is the probability of heads after learning that this is indeed the first awakening? And the hint is this: go back to the logical foundation and its implications in part 3. And the answer is incredibly easy.